I'm coming, as I said, first of all, I would like to thank you all for being here. This is quite an audience here. Thanks as well to all the organization that is here. This is something that as soon as you start to realize how much work goes behind the scenes on trying to have an event like this, you're really appreciated and something you value. And that is so big thanks as well for those people. And basically, I'm coming from here, the European Organization for Nuclear Research. So I will try to, probably for those that you know me before, say what's this guy here doing that usually came here and talked about tactics and ventilation, fire suppression, and what's he doing at CERN. I'll try to walk you through that process and how there is this link between fire safety, fire engineering, that fire intervention tactics, which is actually for us, firefighter safety, and we're all committed to that. So big thanks for the organization and everyone involved, the guys behind the scenes. I don't know the names, but big thank. And before going into anything deeper, I would really like to pull this out. And the reason why is that we're all coming from different countries. I'd like to push and convey the message of how important international networking is. So you guys are coming from, I've seen some of you coming from there, here, all over the place, over here. Right now you'll have a guy that was born here, graduated from there, lives there, works over there, and so on, and had plenty of influences of friends that he's got all over the place. And this is something, without going into particular names, I would really like to stress the fact that how important an international network is. Right before we had Lena that was actually bringing up how international fire service throughout Europe came and helped Sweden in these forest fires. Well, the same thing was backwards, or was in the other sense, when we all were fed with this fire knowledge that was sprouting out from Sweden, and it was spread all over the Europe. So networking, international networking, for me, paid a lot back. Just a strong believer, and I think we need to push that message and keep it going. So that's my first slide on this particular thing that I think is so important. So what I'm bringing today, as I said, this is performance-based design for firefighter safety. So usually say, well, what's the link? We'll see what's the link between fire tactics, which is the topic where I worked for, I don't know, almost 20 years, and then how this is linked to that. And we'll see how that is done in a very peculiar facility, CERN, which most of you could be proud of, because it's a facility that is being funded by the taxpayer money of everyone here, or most everyone here. And we'll see how we try to account for firefighter safety in one of those environments. So we'll try to explain as well where I come from and what is CERN. So for that, I'll pull out some videos and photos. I'll probably do a much better job that I can. So my background is civil engineering, vocational firefighter since I ever remember. So I became a fire officer in the surroundings of the city of Madrid in the province of Guadalajara. I was very early involved as a fire instructor, and this is where, for me, the key issue was firefighter safety and being effective and efficient in the fire ground. So that has been probably my main line of work throughout the years. And then almost 4 years ago, I moved to Switzerland, and then I serve as a fire officer in CERN Fire Brigade. So we'll see what CERN is and particularities of CERN and Switzerland as a fire context. And very recently, a couple of years ago, I moved as a fire safety engineer to the fire safety engineering team, trying to bridge a gap actually between that fire intervention and fire safety engineering. So we'll give you a flavor of what I've been doing there, and how important as well is to have as well the other side of a picture, the other side of a coin. CERN, beautiful mountains in Switzerland. That's the Alps back there. So this is the Lake Leman. And CERN, particularity about CERN is we produce high intensity, high energy beam, proton beam, and we are able to put those beams and trying to collide those two beams and then crash matter actually to see what's inside. We'll see a video later on. Well, to do that, you need actually several rings, several tunnels that lay underneath the between 20 and 100 meters underneath, and that is a 27-kilometer ring. I would actually have to start over here. The very first accelerators that we had were very little, and they could, I mean, they could be hosted in just a room like this. But the bigger the energies, the bigger the challenge, and as we were able to solve some of the pieces of that physics, we went into bigger accelerators that was built in the 60s. And today what we'll see is how we accounted for fire safety in this facility that we have to refurbish. And then lately, that was in almost 2000 that we built the LHC, and that's where that helped to find the boson Higgs. Okay, so a little video that will probably you can read it between the lines, and you'll see how CERN is not only important for nuclear research, but it also has a very important role in politics and a very important role as well in the development of technology that actually leads to being able to have this kind of machine. So I hope the sound works. It's not in French, sorry.
Europe is still recovering from the Second World War. Everything needs to be rebuilt. To revive fundamental research and to stop the brain drain, Europe needs to equip itself with modern research facilities.
Seul un laboratoire bien équipé attire les physiciens expérimentateurs, évite la dispersion des talents européens et suscite l'apparition des forces latentes.
In 1952, under the auspices of UNESCO, the Conseil européen pour la recherche nucléaire is founded. The acronym CERN is born. The CERN Convention is signed in 1953. It stipulates that the research carried out must be purely scientific, not used for military applications, and that all results must be made public. In 1954, construction begins in the Geneva countryside, and the convention is ratified by the 12 founding countries. The European Organization for Nuclear Research is created, but the acronym CERN remains. Under the CERN model, physicists remain employed by their national institutes, but can use the tools that the organization provides. Each country is able to keep its best minds. The laboratory's activities develop quickly. The increasingly large accelerators soon extend into French territory, so CERN becomes the world's first cross-border laboratory, an excellent symbol of science unconstrained by national borders. The purely scientific nature of the research attracts physicists from many nations, despite the political tensions between them. During the Cold War, CERN is one of the few places in the world where Western and Soviet scientists work side by side. Following the ideals of its founders, the laboratory contributes to strengthening peace in Europe. CERN's facilities also attract scientists from other continents. From the 1980s, LEP, the Large Electron Positron Collider, and later its successor, the LHC, or Large Hadron Collider, each of a size and complexity never previously seen, mark a new stage in the globalization of particle physics. New countries appear on the map of CERN's collaborators. Talent and expertise know no boundaries. manufactured by the best industries in the world. And in the other direction, the LHC sends its data to computing centers in dozens of different countries. Today, CERN is a truly cosmopolitan laboratory where more than 10,000 researchers of over 100 different nationalities exchange ideas and work together. Since 1954, CERN has allowed nations to communicate through the language of science. Its model of cooperation, originally dreamt up to rebuild Europe's research capabilities, has now become global and remains an example to others.
Okay, so this is CERN. I'm going to show you some pictures how it looks like. We have standard buildings. Standard buildings would probably look like any other city anywhere. Probably have the biggest hotel in the city of Geneva, biggest restaurants in the city of Geneva. Then we have the research facilities. This is the CMS detector. You can see that's 30 meters high. Okay, it's 30 meters wide. It's a cubicle of 30 by 30 by 30 meters that lays 100 meters underground. Then there's this little piece over here, and this is one of these caverns over here. You can see this man over here. You can tell a little bit which is the size and the challenge that you would find if we ever had a fire. So having a fire in any of those components over there, you can imagine how it is, how of a problem it would be. We have funny things as well, like this antimatter factory, and yeah. So this is some of the stuff that's being built at CERN. And of course, we have a fire brigade as well. We have a fire brigade started in 1956 as a detachment of Paris Fire Brigade. It's a fire brigade that's strongly influenced by Paris Fire Brigade still, and probably half of the members are still going through Paris Fire Brigade. And this is how it looks 4 or 5 years ago. Firefighters coming throughout Europe. And this is probably the key. At that point, there's 58 people in the fire brigade, 12 nationalities, 2 official languages, and I would say another 10 non-official that are spoken throughout the fire station. So it's a unique environment, as I said on the very first slide, to actually have to booster that collaboration, international collaboration. We all come from, or most of us come from a fire service. So we think that when we have a successful company in fire safety, we're successful in the fire ground, it is because we were there, and it's teamwork and excellence of the team, and we made it happen. So there's a very nice picture over here. There's a traditional Catalonian human castle, and it's all firefighters. In order to succeed, well, everybody has a role, and even the guys over here just protecting if someone falls. So very significant picture, but this is just the side that we have usually as a fire brigade. But there's a lot more into this. So fire safety outcome is something that is very related to fire education, to fire prevention, fire protection, fire safety engineering, the codes, the standards, and you name it, it's over there. I'm sorry because this doesn't show, it seems the screen is shorting out on that side, sorry on that. Firefighter training, well, all of that at the very end is going to make it happen. It's going to play a very important role on that fire safety outcome. And it's going to have also a role in firefighter safety. So how can we account, my question over here, and this is how I relate it to my background in tactics, is how can we relate this to, or how we can account for firefighter safety in such scenarios like the scenarios that we saw before. This is the question I was asked when I came to CERN. So you guys, you need to tell me that these guys are safe once they go into the accelerator. What we need to put in place for that to happen. How are we going to analyze this problem? So there's 2 approaches you can have for this. You can either go and follow prescriptive codes and say, okay, we're going to follow the codes, and eventually, I mean, we're supposed to be safe. Problem with that is clear is that probably the code was never meant to be used in an accelerator machine like the one we have. This is at least the first challenge we're going to have. Or either we go and say, let's use a performance-based design. So we'll see what it is. We're going to make a design, a trial design, and we're going to try to prove that that design is safe for firefighters. So the fire safety engineering approach is something that is fairly used in many countries to account for property protection, for building protection, for the contents, for the evacuation purposes, but less used in terms of firefighter safety. So my goal over here today was to bring a little flavor of what we're doing, a humble approach on how we are trying to start to apply this PVD, this methodology into firefighter safety. Tell you that this is a joint effort between the fire brigade you just saw, the fire expertise, the fire experts, and the fire safety engineering team at CERN, and that we have a very precious collaboration with some of the people that are among the audience today, which is the Lund University, the European Spallation Source, ESS. We have a collaboration in Fermilab as well. Go back to slide number 1 where I said how important it is to have that international networking. It's been extremely useful, not only as a peer review, but also actually to put our feet on the ground when things were getting off track. Good. So as I said, this firefighter safety is something we're very concerned. There's a raising awareness, probably due to an evolution in society. We're being taken. It's something we don't accept anymore. It's something that maybe 20, 30 years ago would be something society was, I wouldn't say ready, but would be accepting in a better way. As of today, this is non-negotiable. This is something that we cannot afford. So having in mind this is the turning point in many cases, as we saw, to see how research, we have excellent pieces of fire research that were actually meant and done for the fire service, and how that research is being transformed into reports that were experiments done by firefighters in collaboration with fire safety engineers, a report actually done for the fire service, and then all of a sudden you see how that is transferred. And this is a piece of an operational procedure of a fire department somewhere in France, very close to Paris. So you see how in a very short time we started moving into that way. So when we build these facilities, at some point there's a fire safety or fire safety engineering effort, and then at some point we should say, okay, how are we going to account for firefighter safety in this facility? And this is where it all comes. We all have complex scenarios, and these complex scenarios can deal very differently. We can have, well, anywhere in wildland, industrial, urban complex scenarios. And probably need to define what's a complex scenario is something that probably it is not the usual standard stuff that we used to, that we all deal with. But in trying to define that, I would say that this is something where we have some safety critical aspects that need to be accounted. And when we have a complex analysis that needs to be done, it's not something that you just go and show up over there and say, I'm going to take care of the fire in this accelerator facility and I'm just going to do a size up. There's no way you're going to be doing a size up in an accelerator like that. There's a pre-planning, there's a complex analysis that needs to be done before you even try to tackle the problem. And probably you're going to need as well non-standard tactics or special equipment that to battle and to put in place. So one of these complex scenarios for us is the super Proton Synchrotron. Okay, there you got it. So this is this ring over here, that brown ring over here. Basically, it's a ring that's only 7 kilometers long, which is little as compared with the others. It's a facility that is lying 20 levels underground. So you see the stairs over there, and this is the stair, how it looks in the inside. There's 2 firefighters training. This is usually usual training, instead of going into the gym, you can go up and down that stairs in full gear. That's something you can do, which is basically like a high-rise put upside down. Yeah, put it that way. So that was built in the 60s, and well, the challenges is the standards that were used to build that were the standards that were used in the 60s. We'll see how we analyzed and we assessed the firefighter safety in that, and how we got, at the very end, 13 million Swiss franc blank check to actually improve the fire safety of that facility. It's a critical facility for CERN because every beam goes through that SPS, and this is how it looks in the inside. That's the typical tunnel in the inside. So imagine 7 kilometers of machines like that, full cables everywhere, around 4 or 5 meter diameter tunnel, and that's a shaft going all the way up. Everything is, for the major part, prototypes, industrial standards apply as much as we can, but not all the equipment goes to standards. This is our complex scenario. Okay, so I'm pretty sure everybody, I mean, this very same approach I'm going to show over here is something we could show as well for some urban interface scenarios where you want to see what is the defense distance that we're going to put in place, what compensatory measures we can put in place. It's actually methodology in trying to assess a trial design and see what is the outcome in terms of safety. Well, particular tools that we need, basically we can't run the fire engine inside the tunnel, so this is as good as it gets. This is a compressed form air system. You see the guys, they're on twin cylinder SCBAs, spare twin cylinder SCBAs, special extinguishers because we have rubidium and other nasty stuff all over the place that we need to tackle with precise elements. This is another auxiliary, the LHC, how it looks like, but fairly European standard if it's not for that special equipment that we have in place. Good. So what's the role of the fire department in all of that? We saw before the picture between 1956 and then 2013. We need to know which is the role of the fire department. As I said before, we think we are the ones who are going to solve a problem over there, but fire safety has to be understood with multiple layers. There is a slide I really like from a colleague, from an Italian colleague, Emanuele Gisi, in which he likes to say, well, we're protecting this, we're protecting the environment, we're protecting people, we're protecting assets, we're building the environment, and we need to make a risk assessment to see actually what happens, and then we need to establish a fire strategy and then put different layers of fire prevention on one side, fire protection on the other side, and basically the fire service, we're just there. We're just at the very end right there. So from that point to that point over there, as soon as we have a problem, then the only response is this over here. We've been failing in some of the layers before. We're basically, in many cases, we're just reducing the consequences of a fire, especially in terms of what becomes in terms of property protection. And we operate, and this is something I would say it's because I come from a fire service, it's probably one of the layers which is the least reliable layer in this whole fire safety concept. When we try to operate, we operate with a risk-benefit analysis. And that risk-benefit analysis, what we put on the balance is, well, what we do for life, what we do for the environment, for property, for the continuity of operations of such a facility or industrial compound. And on the other side, there's how much risk we want to bear, how much risk we want to play with, and that's firefighters' safety on the other side. So that's a balance, and that's why probably we need to focus as well in some of the layers that I showed before. So to actually measure, to actually account for that, as I said before, you can go into prescriptive codes. You can say, well, this is what you need to be respecting to be in the codes to account for firefighter safety, or you either go and you have that engineering approach in which you analyze the problem and you see that actually the facility proves to be safe enough. Standard facilities like the one we have over here, okay, that's a building we use. There's tons of research. That's a physicist building, and that's 6 floors and full of really bright people doing physics there. So for that buildings, probably we can follow the codes, either Swiss, either French. In this case, for this building is in Switzerland, so we follow the codes, and usually the outcome is fairly good. Okay. However, then there's this magic paragraph you will probably see in many of your codes as well. And this magic paragraph is, okay, whatever you do in terms of building, you either France, Switzerland, or European Union, there's these magic words that say the safety rescue of teams is taken into consideration. But how? This is the question there. This is very good to be stated in some of our applicable prescriptive codes, but we need to know how we're going to put for that, how we do it. This is where, at least, I know our colleagues from the other side of the pond, from the US and Canada, how you deal with that, or Australia. But in Europe, we have a major issue with this part over here. So that how means what are the limits, when I'm safe to go into firefighting, when I can do firefighting, when I have to lose the structure, when the organization has the right to say that they can count on the fire brigade, on the fire service as part of their fire protection strategy, when they don't have the right to do that. That's part of the whole thing. How big the crew size is, what the resources are going to be deployed, well, that is part of the questions that we need to be asking. And on top of that, we have, as we said before, these scenarios where there's no way you're going to be able to apply prescriptive codes and actually they're never meant to be like that. So PBD proves to be one of the approaches that we're trying to implement at CERN to account for this problem. This is one of the missions I was given as part of the fire safety engineering team. And the idea is to prove it. And to prove it, we're going to see how we do testing, how we do field test, and see which is the performance of a fire brigade. We're going to do modeling, FDS modeling, see actually which are the conditions for the firefighters going inside when they show up. And we're going to run as well probabilistic models to see which is the chance of putting out that fire. And in this case, we'll see it later on, but see for this case, for 90% probability, it will take 68 minutes to put a particular fire scenario out. So this is, we need to know how long it's going to take us, what are the conditions when we show up there, and what's the performance, put all that together. And this is the approach. This is, as I said before, first approaches that we're going in that way. So there's a lot to learn, so be open as well to see what you guys have to say on this. As a basis, we see in the performance of the NFPA guide on performance-based design. It was a very simple scheme that makes lots of sense. You need, I mean, it's something you do since very little when you try to build something. Basically, you build something, okay? You want to say how it's supposed to perform, you test it, and if it's good, it goes along. If it's not good, we'll just turn it around and turn it around. So when it comes to firefighter safety, this is basically a similar process. We're going to have a project, that facility. We're going to establish which are the limits of firefighting. We're going to establish these safety goals and acceptance criteria, what we think it would be okay. We make a trial design, we run, we assess the firefighter safety, and we do that process until we get a valid design. This is the whole process. To be able to do that, as I said, it's a joint effort in which we need professionals, and this is why I'm bringing this, and this I think is relevant to you as well. As members of a fire service, there's got to be someone from a fire service to actually assess and provide the info and the input to the fire safety engineers so that the outcome is something that makes sense on the fire ground. Assessing firefighter safety. This comes to the probably the critical problem in the whole process. Everything else you can figure it out very well, but there's this thing which is acceptance criteria. Acceptance criteria is going to be at the very end, the measurements, that engineering data that's going to tell you that's measurable and where you're going to draw a red line into what is acceptable and what is not acceptable. And for all means, this is something you have to have before you even start to do an analysis. I mean, otherwise it'd be very easy to cheat. You go back here and say, okay, I go through this process, and because the assessment is not good enough, I'm going to change the acceptance criteria so that it's good to go. Well, it's not the way it should be done. The way it's done, you state your acceptance criteria, and then you start running that process to prove that you never get to conditions that you're never meant to be. We, at the very end, after analysis, we broke these two into two categories. The first one will be building specifications, and the other one, exposure limits. Okay. The first one, building specifications, something as simple as, okay, what's going to be the fire resistance, the structural fire resistance of the facility? Are we going to have hydrants? Are we going to have, which is going to be the fire propagation or the compartmentalization strategy of the facility? What kind of fire suppression means we need at some point? What's the evacuation? What are the resources that we put in place? So some of them can be actually stated as real building specifications, where you have it or you don't have it. Do you have a water hydrant? You don't have it. That is as simple as that. And then it comes to a second part where we were looking into the, I'm sorry, this is still on the building specifications. This is the guys from Melbourne Metropolitan Fire Brigade, how they followed a very similar process. This is a guideline, a performance-based design guideline, Australia, early 2000s, late 90s. So it's hats off, because it was very early in time that this was being already applied. And then we have another beautiful picture by Lars, by the way, and which are the exposure limits of that for firefighters. So at this time as well, we needed to go back to see what had been done before, and it was actually as well the Australians and the British that had stated some exposure limits linked to air temperature, to visibility, to humidity, to incident thermal flux, to airflow, and conditions were actually those conditions that was the line between being able to do firefighting or not. And this is very important as well, because we are supposed to design a facility in which we will never get to these situations. This is the challenge. And this is where the fire service as well, I think, has to push as well and say, okay, as soon as we have a facility which is something which is not standard, not normal, please prove I'm not getting, if you want me to go in, okay, otherwise if I'm going to stay outside, I don't care. But if you want me to go in, just prove me that there are some situations in which I will be never exposed to. So this is a little bit, there's a full document on that. I'm going to go into detail on how that was all transferred into our acceptance criteria. But then right now what I would like to see is, I would like to show you is how we did it with this super Proton Synchrotron at CERN, that accelerator. We're missing some lines over here. It's a 11 million euro project. So basically our mandate, the organization provide a mandate first to assess which was the fire safety situation of the facility. During that process, and you'll see, you will not be surprised, we identified firefighter safety as being a critical factor, and we needed to support, we wanted some compensatory measures and some changes in how the facility was done, and that was going to cost a lot of money, and we need to prove, in order to get that 11 million euro check to do that, we need to provide a very nice justification, a very solid justification. You see part of that. Project is absolutely driven by firefighter safety. The study phase was already done, and we are starting to implement those elements. As soon as this accelerator stops this Christmas time, we'll be going down to put all those elements inside. So this is, as I said before, we're in the very early stage of that PVD process, in which we have to look in what we have between the hands, and that's the facility, that's the Super Proton Synchrotron. This is how it looks like. I'm going to step it a little bit like that, probably better for me. So around 1.1 kilometers between different shafts. This is the brown ring over here. Okay, we're looking into an average depth of around 60 meters there. And this is the link, the different tunnels linking to other facilities. And as of today, it doesn't have any compartments whatsoever. It doesn't have any fire suppression whatsoever inside the tunnel. There's some on the shaft. PVC cables, big density. That's what we have. Okay, so just imagine you're supposed to go down, put out the fire, and get back safe. So imagine what was the kind of assessment, the presentation I had to deliver to say, well, I'm afraid to say this is not possible. This is not something we can do. This is how it looks in the inside in the 70s. It still looks the same way. Okay, nothing changed in the inside. And what we will find inside is we have a fairly good fire detection system based on air aspiration, air sampling. We have some sprinkler from the 70s in the shaft, but other than that, there's no water supply, there's no means of water in the inside. There is extreme limitations into firefighting as would understand it. Situation as well is that we have a fire brigade with very limited resources. This is what you will have on duty every day. It's a fire engine, an ambulance, an extra guy with a multi-purpose vehicle, a control room that is controlling all that fire detection system, and that would be dispatched as T equals 0. As soon as we have a fire detection, we'll be able to get our friends from the Swiss side and from the French side after 30 minutes, but they will not go inside. And that's something clear. They will not go inside. They don't have to train. They know the facility. That is something that is, it's fair. And we can have even more Swiss and more French, and we can have even more CERN crews after an hour. That is the reality of what we have. So I'm not going to go into the assessment that we presented, but you all will probably have very good ideas of what you think of the situation as it is. It doesn't look very, probably, as I visited the first time, I was in the first time and said, well, this is probably one of the most challenging scenarios I've ever seen if I ever had to come inside. So in this whole process where we fix our fire safety goals, we were looking into fire safety goals regarding life. There's some physicists in the inside and maintenance people. Environment, it's very important to see what is going to be the release into the atmosphere, because it's not only smoke, but the thing is that the smoke that we are releasing to the outside is radioactive. Okay, those cables have been exposed to a beam line, to a proton line for 40 years, so they become activated. So if they burn, actually what you burn is radioactive material that will go outside. Okay, so we need to do something. In the environment, that is a very important, a critical a critical life safety objective. But also, usually as a fire service, we tend to go and, well, property is important, but it's something that is usually in scale is way down low, because at the very end, it's also insured, okay, it will be covered, someone will pay. With the machine that we're talking about, it's a machine that is the result of 60 years, 20 plus countries putting money in. It's not a machine, it's not something replaceable, something you can go off the shelf. We're going to get another CERN machine over here. It's something we'll actually have to rebuild the factories that build those magnets that you've seen inside to actually put it back into work. So this property, it's got a very important factor. And then the continuity of operations. If we stop that, then everything falls and everything stops. And this is something, if some of you related a little bit with the industry, will find this very important. But we are here for firefighter safety, which is the one of the critical safety objectives as in terms of life safety objectives, and rescue teams shall be able to intervene safely and according to current standard operational procedures. So, and that transfer, as we said, into building specifications that meet our standard operational procedures as well, and exposure limits. We're going to see some of the building specifications that went into this case, for example, and these are some of the areas. I'm showing some, this is sort of a snapshot of the whole thing. It would be too long to expose. So one of the things is that we need a safe area. We can't go 1 kilometer, then 100 meters down, 1 kilometer, and then going back. I mean, where is the limit with the twin cylinder SCBA that we're carrying on top? How far can we go into the fire? How far can the fire be? Make it to the fire, work on the fire, and then make it back, but still have some time to bail out if something goes wrong, reserve. Well, we'll show you how we ended up with those 450 meters. We also need to match, the fire scenarios that we have. We're going to have fire scenarios that need to match the extinguishing capacity that we have. And this is not a free thing like we would have probably in surface fires, because that little engine that you saw, that little tractor and trailer with a cab system, it can cope with a 5 megawatt fire on those cables for if the seat of the fire is limited. But if we're looking into bigger scenarios, that won't help. So we need to, at some point, put a limit. We have this rear gun, or this is our fire suppression means, well, we're not supposed to find fires. We'll overcome that possibility. Otherwise, you put walls, you fire compartments, you give me another means. Communication, structural stability, stuff like that. So, as I say, this is one probably, when you're dealing with these tunnels, structures, accelerators, this is one probably of the biggest challenges that we have. You need to make it to the fire from a safe point, okay? Then work on the fire, make egress, and have some reserve. And basically, that engagement distance over here is going to drive the whole process. Whether we have fire doors in place every once in a while, and we say, well, after 2 fire doors, we can presume the atmosphere is going to be clean enough so that we can take our SCBA out. After 1 door, we may have smoke still in this area, so we can't count on that. So how long is it going to take our operations? And then we did several field tests, and that was reported, bringing in hoses up and down, reaching the seat of the fire, walking out, having in mind as well the possibility that that tractor that you saw on the pictures doesn't work and we need to walk out then. So having in mind all that, say, well, 450 meters, that meant that with the current SCBAs that we had, and for the standard firefighter we have in our fire brigade, that meant 10 minutes to work on the fire in a safe way and being able to make it out and still have a reserve time to bail out if something goes bad. Well, this is how we set some of the acceptance criteria and how we dealt with it. So the idea is that this is how the facility looked today, and this is how the facility should be looking in the future, in which we have these doors every once in a while, where you're going to see as well that there is a standpipe over here, dry riser. They'll bring water all over the accelerator, where you can have outlets as well, very close to the fire doors. There are some other outlets as well in between compartments, but you can actually deploy a tactic inside, given those requirements, building requirements, facility requirements that stated. Then it comes to, okay, we have this, we've chunked out this facility, but we need to see for the different fire scenarios that we're going to have, because fire can happen here in the shaft. It could happen as well over there, so right there. It could happen in the middle of a section, so anywhere. We need to see how far we can get, what kind of fires we're going to get. So this was the original situation, and this was part of the original presentation I used, in which this red area basically is a red area is a place where if you make it in case of a fire, and a standard fire with a return period X over there, you're going to make it over there to the fire, but you're never going to make it back, because you won't have air enough to get it back. So this green part over here, you can fight the fire. Over here, you would be able to reach the fire and get back. And if you have on the red area, once you go there, it's like if you were diving and you went too deep and there's no way you're going to make it back. Okay, so new scenario, new situation, everything will turn green or orange, which is good for us. Again, as I said, matching the firepower as well, different strategies into what the fire size that we have, and what are the resources that we have, and what's the approach, the tactical approach that we're going to have in those. So whether you have a very small fire in which, because property is so important, we need to actually put the fire with the extinguishers. Sometimes we have a bigger fire and then we'll use that trailer, or we jump into scenarios in which we'll need water. So all these matching resources as well turn out to be were shaped as well after the means that we have in place. We saw that trailer that we had before, and that was tested using the kind of cables that we have over there, trying to reproduce the conditions, the density of the fires that we'll be finding in that tunnel, seeing when that was possible and when that was not possible. Some criteria that we came up with because of that, instead of so depending on the type of fire, the matching resources, suppression means, and well, the fires change a lot, and you can have cable fires, very high density cable trays where you would have very high heat release rates. You can have experimental setups like that. You can have transport devices like that, which is this one here, by the way. It's got 1,000 liters of oil inside as well. So you need to account for that as well. And all that fuel load inventory goes into a heat release rate curve. And that heat release rate curve is introduced and is simulated into the different scenarios that we have. So whether we have the fire, as I said, in that shaft, whether we have it in a piece of a tunnel and a chunk that is bigger and longer, well, but we need to put all that in and model. To model, I will advance on this, and we're using basically two tools. One of the tools is FDS, or you guys probably very used to it. We introduced that fuel load inventory, that design fire fuel load inventory that we had that yield that design fire into that geometry, and we got this funny I hope there is a video over here. So this is one of us facilities, and we can actually see how long it will take, how we will lose visibility, what would be the conditions, the thermal flux, the temperature, everything we need by the time the fire brigade shows up. But when is the fire brigade going to show up? This is something that we need to model as well. And the way we model that is trying to bring a fire response probabilistic analysis model, which is a complex tool developed at CERN by the team, in which we can count all the different pieces that take part in between the fire breakout and actually the fire. When fire is extinguished, we have to detect the fire, we need to turn out, to travel up to the surface, to make access all the way and get to the fire, and finally do a manual firefighting over there. In between, we may have a sprinkler system in action. We may have a robot. We have firefighting robots as well in the facility. So all of this will be able to let us know with different probabilistic functions, with different distribution for each of those modules, will let us know that for a given layout of the facility, a given design fire, and a given design, fire protection design, would be able to say, okay, this fire with a 90% probability is going to take us 64 minutes to put out. And then we can go into the simulations and say, well, when you show up right now, well, the conditions are going to be like that. And if those conditions aren't good enough, then the trial design has to be redone once again. This is the actual process of that fire response analysis model. So this is how we, at some points, would say that it goes into state-of-the-art simulation, a lot of calculation, and then, but at the same time, you need to bring all this in and try to put it and make it sense into your background. So we had this process going on for this SPS facility. We had the acceptance criteria. Not only this, there's a whole bunch of acceptance criteria that we needed to match. We had different fire scenarios, different clusters of fires and design fires. We did the simulations, and basically what you go into is you run the model, you see where you fail, and because you fail in this one here, you need to go back again, redo, and say, well, we're going to install some fire suppression means, we're going to install some fire sprinklers, we're going to put a robot that's able to tackle the fire before, and then redo that simulation process, that whole assessment process, to actually see whether that design is valid or not. So wrap up on this. This is a parallel process to prove that the facility is safe for firefighting. I think, which is very important, and come back to my first slide here. It's very important that in order to have a fire safety outcome that is a success in times of fire intervention, we need to be all on the same page, and it takes a lot of fire prevention, fire protection, needs also fire education, we need fire safety engineering, and we need to work together actually for these men to be successful, but as a whole. So thank you very much. If you have any questions, I'll be willing to answer all of them. Thank you.